Good evening, everyone. Welcome to the Tucson Amateur Astronomy Association December meeting. We're so glad to have you here. We have people in person in the meeting. We have guests that are attending via social media. And of course, we have our people on Zoom. So we will be moderating all of that throughout the meeting today. And if this is your first time in a TAAA meeting, we are just delighted to have you. We will start soon with our first presentation. Tonight, we have one speaker who is going to give a nice in-depth talk for us. And afterwards, then we will say goodbye to our guest in the meeting with us, and we'll continue with a meeting for our members, in which we will have some more in-depth information that will be presented by the guest speaker. The first part of this meeting will be recorded and will be available later on YouTube. The second part of the meeting has some information in it that is not for public release yet. And so it will not be recorded and will not be broadcast. We do ask that you keep your sound turned off so that other people are not hearing extra noise. And we ask that people in the room where the meeting is occurring also not talk, because the Zoom will pick up any talking that occurs in as background sound in the meeting. We also ask that if you're on Zoom, that if you're going to be moving around a lot or doing some distracting, that you turn off your video for that activity. We're going to, and I'm May Smith, I'm the TAAA president, and we have with us tonight Terry Lappin, who is going to be, I think, helping with Facebook tonight. Jim Knoll is going to be helping with our social media and with some of the Zoom activities. And then we're going to have Bob Rose, who's also going to be operating the camera for us. So we have a lot of electronic support for our meeting tonight. We are going to go to our guest speaker now. Our guest speaker is Rebecca Levy, and Dr. Levy is not related to David Levy, who is a member of our club. But Rebecca Levy is at the U of A, and she's done some really significant research in her work, research studies, and as a faculty member at the U of A. And she's going to talk to us now about a JWST view of starburst galaxies. So she's going to talk about, lots of upcoming data possibilities. So Dr. Levy.
So hello everyone, my name is Rebecca Levy. I'm a postdoc at Stewart Observatory, and I'm really excited to talk to you today about the JWST program that I'm very involved with. And before I dive into what I hope this program will learn from the two galaxies that we're studying, why those two galaxies are so special. And the two galaxies that we're targeting for this program are M82, Cigar Galaxy, and NGC253, the Sculptor Galaxy. And again, I'm sure we're using amateur astronomers in this room, and a lot of you are very familiar with these experiments. So I'm going to give you a little bit of an overview about why we picked these two galaxies and why it's worth studying them in the first year of observations with JWST. So I'm going to start with some brief background, and I'm going to start with M82 because it is arguably the more famous or well-known of the two galaxies. So M82 has been known for a really long time. It was discovered in 1774 by previously 1774, he was looking at the constellation Earth and Nature, and in his writings he noticed two small dots, two small nebulae above the ear of Earth and Nature. Now, when Bode was making his observations, we didn't know that there were galaxies outside of our own. We didn't even know that we had a galaxy. And so anything that wasn't a star or a planet or a comet got classified as a nebula. And these were basically fuzzy blobs in the sky. And so he noticed two of them, and he noticed that Vega, the smaller, fainter of the two objects, was very pale and fluffy. Here, and this one was decidedly not. And so in the intervening few hundred years, we learned a lot more about M82. This is a more modern day view of this system. So M82 is up here on the screen, and it's a group. It's called Starburst Galaxy now, and M81 was the bright blobs that Bode saw in his telescope. There's also another smaller dwarf galaxy in the system here. Not necessarily both of these galaxies are actually related to one another. Distances are a really hard thing to measure in astronomy, and so it could be galaxies aren't actually related to one another. It's just a chance projection along the line of sight. In fact, one of them is much more distant, for example. But one way that you can tell that these galaxies really are related to one another is instead of looking at the starlight, you can go to much longer wavelengths and look at the gas in and around these galaxies. And that's what's shown in this image. This is the cold gas in and around this system. And so clearly these galaxies are related to one another because back and forth galaxies as they're interacting. And it turns out that this interaction has a major impact and consequences for our friend M82. M82 is much smaller than M81, and so it's much more impacted by its own large neighbor. And one of the impacts or consequences that this interaction has on M82 was discovered in 1963 by Linz and Sandage, who are at the National Observatory just across the street. And in 1963, they discovered what they call an explosion in the center of M82. So this is an image from their actual beaker. And so the disk of M82 is this sort of long, thin structure extending across the stream. This galaxy is long and thin because it's almost edge-on in our view. We think it's actually a disk and would look more round, but it's inclined to our line of sight, and so it appears as this very elongated structure. But what Linz and Sandage discovered was all of this stuff above and below the disk of M82. And they were able, from these observations, to measure that not only is there material there, but it is moving away from M82 very rapidly, and it's carrying an enormous amount of energy away from the system. And so they were able to conclude that approximately 1.5 million years ago, there took place an extremely material of the center of M82. And it's this expulsion of material you see as this massive outflow coming from the galaxy. So this sort of begs the question, what triggered this expulsion of material? On astrophysical timescales, 1.5 million years is really short. So how do you move that much material out of the galaxy on a short timescale? We now know that the answer is that there was a burst of star formation, a rapid increase in the rate of star formation in the center of this galaxy. And we term this phenomenon no, and it's something else really cool like this. And so come about. One, how does a galaxy suddenly increase the rate at which it's forming stars? In the case of M82, it was something like 10 times, but other galaxies can do this by a factor of 100 or 1,000. So how does a galaxy rapidly increase how many stars it's making for a short time? And the second question, or I guess the first question, is how do you form a star in the first place? So taking the second question question first. How do stars form? Everything starts with a cloud of gas in the galaxy. On the slide, I'm showing some examples of gas clouds in our Milky Way galaxy. And all of these clouds are either stellar nurseries that are currently forming stars, or we think will form stars someday. You might notice recognize a couple of them, especially in the first creation down here. So nature is a much better artist than I am. And so I'm going to enable structures as this boring cloud here. That's what I can do currently. So how do you form a star? Well, you start with this cloud of gas, and what you want to do is you want to compress it. You want to shrink all of that material down and make a star out of it. And so within the cloud, there's a balance between gravity, which is pulling everything together. The clouds are made of molecules and atoms, and so they have mass, and gravity wants to bring all of that material down to the center of the cloud. The same way that I'm standing here on the Earth, I'm being pulled towards the center of the Earth. Gravity wants to pull all of this cloud material down to the center of the cloud. That's great. That's a great way to compress a cloud, have gravity pull everything to the middle of it. But because this cloud is made of particles and it has some temperature, those particles are all bouncing around. And that's part of the force of gravity. And those two things balance each other and keep the clouds relatively stable. So in order to form a star, you need gravity to win. So how do you get gravity to win in this scenario? The answer is that you make the cloud very, very cold. So when molecules and atoms are cold, they don't move around as much. And so that pressure term drops off really quickly. And so when you don't have as much pressure, gravity wins. And in fact, it collapses the cloud in a runaway cascade. And so the cloud collapses, it gets denser, and collapses, and gets denser, and collapses, and gets denser, all the way until it forms, the material is so dense that it can start nuclear fusion, and start fusing hydrogen into helium. And at that point, you have a star, and the pressure from that nuclear reaction stabilizes it so that your star is a nice, stable, glowing ball of hot gas. So that's a very simplistic way of how you form a star in a normal circumstance. So then how do you suddenly ramp this up? How do you suddenly, and for a brief period of time, increase the rate at which stars are forming in a galaxy? Well, one way to do that is to increase the amount of cold gas in a galaxy. This is the fuel for star formation. So if you have more fuel, you can form more stars. It turns out that's not quite enough, because even though most of what a galaxy is doing is making stars, galaxies are really inefficient at making stars. Only about 1% of the gas in a galaxy will turn into stars under normal circumstances. The rest of that gas goes back out into the galaxy. So the other thing you need to do is you need to increase that efficiency. You need to help the gas collapse easier and more completely, and keep it in that environment where it can continue to collapse rather than having it escape into another part of the galaxy. And so the way that you're going to increase its efficiency is by applying some pressure from the outside. So it's like giving the cloud a big old push and helping it collapse faster and more efficiently and confining that cloud so the gas can't escape. So where does this pressure come from? Well, there's at least 3 sources that we can think about in terms of galaxies. The first is if you crash 2 galaxies together in a galaxy merger, the stars in those galaxies don't collide when those galaxies merge, but the gas there does. And even if the gas doesn't collide, you now have a lot of gas in a much smaller region of space than you used to, and those gas clouds will push on each other and encourage each other to collapse very quickly and efficiently. And if you notice in these real images of galaxies that are in the process of merging, everywhere in these images that's blue is where new stars are being formed. And you'll notice that that's throughout the entire galaxy. It turns out you don't have to be quite as dramatic as slamming the galaxies into each other. There's more mild versions of this interaction, called a tidal interaction, which is the case for everything too. The streams of material that are going between the galaxies, that's enough pressure to encourage the gas in these systems to collapse further, triggering this starburst, this enhanced star formation. And again, you would expect that star formation to be sort of distributed across the galaxy in that case. The final way that you can do this is a little bit different going to spend some time talking about it. You can get a starburst without needing any companions, without needing any other galaxies. And the way that that happens is sometimes when a galaxy has a bar. So this is an example of two spiral arms here, but it also has this feature in the center called a bar. The bar is distinct from the spiral arms. It's not just an extension of them, it's a totally different kind of thing. And I like to say that bars are gas highways. Bars are incredibly efficient at taking material from the outskirts of the galaxy and funneling them down to the center very efficiently. So much like if you're taking a freeway system into the center of a city, much faster to use the highway than to use the surface streets. And the similar thing is true in a galaxy. Now, if you've ever been going downtown on a highway for a big event where there are lots of other people going to the same event, you know that when you get off the highway in the center of the city, you end up in a massive traffic jam. The same thing happens in the centers of galaxies. You have all of this material streaming in along the bar, and it winds up in the center of the galaxy, and it all piles up, and it forms a gas traffic jam. And when you have gas piling up and compressing against each other, you get a starburst. You have all of this gas in the center of a galaxy compressed together and concentrated there. It's very hard to remove gas from the center of a galaxy, so all that gas basically stays there. And you can increase the efficiency with which you form stars and trigger a starburst. Now in this, what we call bar-fed starburst scenario, all of the star formation, the new enhanced star formation will be concentrated only in the center. And so in all three of these scenarios, we see dramatically increased star formation compared to normal galaxies like the Milky Way, for example. And as I mentioned, this tidal interaction case is how M82 is undergoing starburst. And this bar-driven case is how JWST-253 is undergoing its starburst. And so I'll introduce JWST-253 now. So JWST-253, or the Sculptor Galaxy, was discovered just a few years after M82 by Carolyn Herschel. So Carolyn Herschel and her brother Mike Herschel on of stars and stellar clusters and nebulae. And on September 23rd, 1783, Carolyn discovered this blob, this nebula right here. So the sky chart from around at the same time, and this is JWST-253 down here. Now, I was able to find an early drawing of the galaxy itself from the mid-1800s by Sir John Herschel, who was Carolyn's nephew. And this drawing doesn't look very interesting in this picture, but I promise there's much more than meets the eye. So what do we know about JWST-253 in the modern day? Here's a modern near-infrared galaxy. So it has two spiral arms, one up here and one down here. This galaxy is also almost seen at nod to us. It's very highly inclined. But in the center, it's a little hard to see this at a time. There's a bar right here. Galaxy has two spiral arms and a bar. And we know that JWST-253 hosts a central starburst in the very center, undergoing this massive increase in star formation. We know that that's fueled by gas that is flowing in along the bar. And again, in this bar-fed starburst scenario, we expect the starburst to be at the center, and that's exactly what we see. And all of this star formation in the center is resulting in a massive outflow of material, like M82, although the outflow in JWST-253 isn't quite as spectacular. On this image on your right, this is a composite bubble image. So this is the center of the galaxy here. And what you might be able to see, people will probably see better, I apologize. There's some trails of brown material coming perpendicular to the disk. And that's dust in the outflow of this galaxy. On the left here, I'm showing a different way of looking at the outflow of this galaxy. So this box is to zoom into the center of the galaxy, where the center of the galaxy is this X. You might be able to see this cone-shaped region of blue color. That is extremely hot X-ray emitting gas emanating from the center of the galaxy. That gas that extremely hot outflow is represented by the yellow stuff, which is slightly cooler, only 10,000 degrees Kelvin gas. And then the white contours are extremely cold, 100 Kelvin gas, and ultimately in the outflow. And so the outflow of these Starburst galaxies, both NGC 253 and M82, span a huge range of temperatures and densities in the same outflow. So I want to go back a little bit to how stars form for a moment. So you might imagine that if you've changed the conditions and the way that stars are forming, you might expect that the number of stars you get out is different. And the answer is that that's exactly what happens. So in normal conditions, from a single cloud, you might form one or a few stars. In a starburst, because you trap all that material and increase the efficiency so much, you instead form millions of stars from each cloud. And groups of stars we refer to as clusters. These are stars that all formed from the same material around the same time. And extreme clusters we call superstar clusters. And these superstar clusters are only found in starburst systems today, but we think they may have been more common in the past. And we answer questions about it. So I want to spend just another second on superstar clusters, since this is one of the things that my research is most closely associated with. So in the background here is an image of a dwarf galaxy that's underneath stars. And these two objects that I've highlighted, those are not individual stars. Those are superstar clusters with more than 100,000 times the mass of our sun, and containing, a million stars or something like that. So these superstar clusters are extremely massive, containing more than 100,000 times the mass of our sun. More than a parsec or less, and the reference 1 parsec is 3.3 light years. For comparison, the difference between us and our solar system to our nearest star, Proxima Centauri, is 4.2 light years. So if you can imagine taking a million stars between us and Proxima Centauri, that starts to get an idea of how dense these objects are. Moreover, if you were in a superstar cluster, the average separation between stars would only be a light month. So, for example, it takes light from Proxima Centauri 4.2 years to reach us. In a superstar cluster, it would only take a month for the light to reach us. And again, 1 light month is in the Oort cloud, so not even really outside of our solar system. So you can imagine having a star out of the Oort cloud. That's the sort of densities that these things are. So these are extremely compact, extreme objects, and they're very, very young. So M82 has a lot of superstar clusters. So here's a beautiful famous composite image of M82. The disk is shown in the green and yellow colors, and then the outgoing material is shown in the red colors. If we zoom in to the sort of center of the disk in the pink box, here's an image from the Space Telescope. And what I want you to notice in this image is 2 things. The first is everything that's sort of brown or orange or yellow. That's all dust. These Starburst galaxies are incredibly dusty, and we'll get back to that in a moment. The other thing that I want you to notice is all of the white dots in that image. These are all clusters of stars. Those are not individual stars. They're not foreground PA stars. Those are extremely massive superstar clusters in M82. If we zoom in towards the center even more, this is the and again, all of these dots that you see in this image are superstar clusters containing more than 1 million stars in each cluster. Now, NGC 253 has superstar clusters too, but they're much harder to see. And the reason that they're much harder to see is again dust. NGC 253 is an incredibly dusty galaxy. In fact, that's one of its defining characteristics, is how much dust the system has in it. And that's really interesting, that it makes it really hard to see the cloud. So the region of this galaxy is underneath Starburst is the region of the box over here on the zoom in of the zoom in. This region of the galaxy is a tiny fraction of the area of the galaxy. But that part of the galaxy is forming as many stars per year as the entire rest of the galaxy combined. And you'll notice from this optical Hubble image that when you look in the you don't want anything. You certainly don't see any superstar clusters. And that's because the dust is blocking our view. So we need to go to longer wavelengths to try to see through all that dust. So here I'm showing zoom in to that central region where the boxes to scale. And this is a near infrared image from Hubble of Cigar Galaxy. And so we can see we're looking at our four gas that's been heated by the star clusters in the center of that galaxy. And so in the 90s, there were 4 clusters identified in the near infrared, showing the red circles. And then this one, the pink box, was later on confirmed to be a superstar cluster. But again, given star formation we know is happening, we still expect to see more clusters than this. We know M82's got a ton of them, so where are the ones in the G353? Well, it turns out that even in the near infrared, the dust is still really getting in our way. It turns out that even in the near infrared, the brightness is reduced by a factor of 1 trillion due to all that dust. If you have ever driven in a dust storm here in Arizona, you know that sometimes a really bad one, you can't hardly see the car's taillights in front of you. That's what we're contending with here, but ramped up by a lot. So to reveal these clusters, which we think are there, we need to go to even longer wavelengths, where we can see through all of the dust. It's not going to block our view anymore. And for that, we need to skip all the way over the rest of the infrared and go straight to the submillimeter almost in the radio to see through all of that. And so this was first done in 2011 by Sakamoto et al. This is an image of that same region seen at a much longer wavelength from the submillimeter array, which is a radio telescope on Long Bay in Hawaii. And what you're looking at here, these 4 clumps, are the sites of intense star formation in the center of this galaxy. And if I link back to the previous slide, you'll notice that that brightest one with red is completely invisible in the near infrared. Again, there's so much dust in this galaxy. Now, this blue stone here is showing you the resolution and precision of this image. And so we can't, what this is telling you is we can't really measure structures that are smaller than about 30 parsecs. And remember, superstar clusters are 1 parsec. So these aren't superstar clusters. We're sort of seeing the smeared out combined light from a bunch of them. So we need to go to higher angular resolution to reveal these clusters. So we can do that with a telescope called Palmer. America. So now you can see with ALMA is better resolution. What was 4 blobs is now 8 blobs, but we're still not at the resolution where we can render the superstar clusters. We can push all that and so we were able to show in this paper that I was involved with. And these 14 blobs that you see here have all of the properties of the population of superstar clusters that are still growing. These clusters are all extremely massive in terms of the number of stars they have, but they have a lot of gas left in them and around them to potentially grow even larger. It's only down to 5 parsecs, which is close to what a superstar cluster is, but not enough to pick them all apart. And we'd really like to be able to do that so that we can measure how many they are, how big they are, how massive they are, without blending multiple clusters together. And so we can push ALMA to even higher resolution, and that's work that I've done in the last few years. So this is now the highest resolution image of the center of G353 that we have. You can see it's not up there. But now we're down to the size scale of half the parsec. And that's smaller than what we think superstar clusters are. And this means that they're not just blobs anymore. They have structure. You can see that they have a shape. It's not just a blob. And this is really incredible. Measure the size and adapt it in a better, more system. Now I want to work a little bit on the resolution of this image because it's really incredible. This is one of the highest resolution images we have in a galaxy outside of our global group, except for the EHT stuff, of course. So the resolution of this image for the amateur astronomers in the room is 28 milliarcseconds. And if you imagine the size of the full moon on the sky, if you cut the full moon into 100 strips, the resolution of one of the size of one of those strips is the resolution of this image. Another way to think about that is if you're flying in an airplane at 35,000 feet and you look out the window, if you can make out the short end of a grain of rice on the ground, that's how good this image is. That's how sharp it is. In physical terms, it has a resolution of half a parsec, which is 1.5 light years. And again, remember that the distance between us and Proxima Centauri is 4.2 light years. So we're seeing it better than the separation between us and our nearest star in another galaxy, which is just incredible. So you might have noticed that these superstar clusters are arranged in a line, and that's kind of weird. It turns out it's not actually a line, it's actually a ring. So in some work that I've done this past year, I was able to show that these superstar clusters, if you could look at them from the top down, they're actually in a ring. And again, it's because this galaxy is inclined to our line of sight. We're seeing it almost edge on. That when you incline this ring with what we think the right inclination is, that's what makes it look like a line to our perspective. But it's actually a ring of star clusters in the center of this galaxy. So what I haven't told you so far, we've sort of gone through this. Starburst Galaxies have sort of two defining characteristics that we can see. They have superstar clusters, and they have these massive outflows of material. But I haven't yet told you how those two things are related to one another. And they are, so let's go through that quickly. So eventually, the massive stars in those star clusters will blow themselves to bits as a supernova. This happens after about 3 million years. And because all of the stars in a single cluster formed at about the same time, and all of the clusters in the center of the galaxy formed at about the same time, that means all of the massive stars and all of the clusters are going to blow themselves up at about the same time, or within a few billion years, which in astronomical terms is about the same time. So for something like the stars in NGC 253, when all of those massive stars and all of those star clusters blow up, they will release the energy equivalents of that many hydrogen bombs, which is 5 with 33 zeros after it, in case you didn't want to count all of those. That is an inordinate amount of energy. And so clearly, all of that energy has to go somewhere, not just going to fit in the center of the galaxy. And this is the source of that explosion that was in Sandage detected in M82. So where does all that energy go? It goes into making an outflow. So the energy wants to escape somewhere, and it is much easier for that energy to escape out of the short side of the galaxy rather than plowing the disk of the galaxy where there's lots of stuff for it to run into. It takes the path of least resistance out of the galaxy, sweeping up anything that's in its way, basically. And that's what produces these huge, large-scale outflows that we see in Starburst galaxies. Now, I want to make the point here that it's not that this is a cyclic process. The current star clusters that we see in the centers of these galaxies are not the ones powering the outflows. There's a previous generation of star clusters that have already undergone supernova that are responsible for this outflow that we see now. When the current superstar clusters in the centers of these galaxies age a couple more million years, then they will, all of their massive stars will blow up a supernova and re-energize this outflow in another wave of material being expelled. All right, now the world explore the supersystems in particular. And now I want to change gears and talk about what we're going to do with JWST. So, for those of you not familiar, JWST looks like this. The schematic of it out of space. It launched Christmas Day last year, and it has been sending out data since the summer, at least for calibration and things like that, science data. So I'm not going to go through all of the technical specifications of JWST. That would take a really long time. But just to sort of be familiar with the both plated and simultaneous. For reference, the Hubble Space Telescope mirror is about 2.2 meters. So this is significantly larger than HST, which means you can collect light more efficiently and you get better spatial resolution. Unlike Hubble, which is in a low Earth orbit here, low altitude, JWST is orbiting the sun, all the way up here, up to on the other side. And so this means that JWST isn't serviceable. If something on it breaks, we can't send astronauts to go fix it. We have to try to fix it from the ground, or find something else. JWST is fine, hasn't had any problems yet, but just sort of a point of reference for where it is actually orbiting. So what are we doing with JWST? So our JWST program is called Dissecting Prototypical Starbursts, NGC253 and M82, and their cool galactic winds. It's project number 1701, in case you want to go look it up. It has information publicly online. The leader of this project is Professor Alberto Pilato, who's at the University of Maryland. And we were allocated 44 hours of time on JWST in its first cycle, its first sort of session of observations, to make these measurements. This is a modest, quite modest investment by JWST, and so we're incredibly grateful to have gotten the time to carry out this project. And I want to make the point that it's not by no means just me and Alberto doing all of this science. We have a team of almost 40 people spanning around the globe at a variety of career stages who will be working on this project. So these are people who helped put together the proposal, who helped us with some technical aspects, and who are already starting to work on the data that we have received. So what exactly are we doing? We have 3 key observations that we're trying to make with this program. The first is we want to take pictures of these galaxies in the near infrared. And we're going to target the entire outflow region, so the magenta box is to scale. We will be taking pictures of the entire region in M82 and GC253, capturing the outflows, as well as a smaller segment over the center. The reason why we need the smaller segment is because the centers of these galaxies are incredibly bright, but their outflows are incredibly faint. And so if you try to use the same exposure to capture both parts, you will completely wash out whatever's happening, anything in the outflows. So we need a sort of 2-component approach to make sure that we detect what we want to see in the outflow, and also we can see stuff in the center to be interesting. We're going to use the mid-infrared imager for a similar goal, or in the same region. In the outflow center within the mid-infrared as well, so it's slightly longer wavelengths. JWST, and we're going to use that to get spectra in the superstar clusters. So until a couple weeks ago, I would have told you, stay tuned. These data are going to be our holiday presents in 2023, a year from now. But we got a little bit of a surprise. Some of our data were moved up in the scheduling queue by over a year. And so in mid-October, we received the central pointing of M82 in the near infrared. The central pointing of NGC253 in the near infrared is set to be observed tomorrow night. And we're hoping that these large-scale maps in the near infrared in NGC253 will be carried out before the end of the year. The rest of our data is still scheduled to come a year from now. So we sort of have a gap in our program. So let's maybe talk a little bit more about sort of what we're measuring, not just how we're measuring it, but what are we measuring? Well, the different filters for the imager on JWST are sensitive to different components of the galaxy. And the analogy I'm going to use here is going to be a packet of starbursts. So imagine your galaxy is a package of everything for starbursts. And you'd really like to know what those starburst candies taste like. So with the imager, you use filters to collect light at a certain wavelength. So in a narrow range, relatively narrow range wavelengths. So filters give you a measurement at one wavelength. And this would sort of be like trying to figure out what every flavor of starburst tastes like, but only the pink ones. That will give you some information about what starburst candy tastes like, but it certainly won't give you all of the information. Spectroscopy, on the other hand, gives you measurements over a full range of wavelengths with very fine spacing. And the type of spectroscopy that we're going to be doing in the infrared gives us a picture of the galaxy or the portion of the galaxy that we're looking at every single one of these very fine wavelength slices. And so clearly this gives us much, much more information than just a single filter, but it's much more time intensive to take these kinds of observations. So the imaging with filters and the spectroscopy go hand in hand. So with the near-infrared imaging, we're using NearCam, which is the near-infrared camera. It's very creative, but it was built here at the University of Arizona, so we're incredibly proud of it. The leader of the lab is Professor Levy. We will be using 6 filters on board NearCam, which are sensitive to starlight, some are sensitive to dust, others are sensitive to shocks. So when gas comes in the middle of itself for each other, it produces shock waves, so we want to try to see that. As well as some components of the gas as well. In the mid-infrared, we will be using the MIRI instrument, which is the mid-infrared imager. MIRI is co-led by Professor George here at the University of Arizona, although it was built at the Jet Propulsion Lab in California, so we're also very excited about MIRI. And the 3 filters on MIRI that we're using are sensitive to the dust in these galaxies in different ways. And so we'll be getting different information about different forms of dust in these galaxies. And finally, we will be doing this mid-infrared spectroscopy, the sort of very detailed information over just the superstar clusters. Again, it's very time intensive, so we can only do this over a small area, and doing it over the superstar clusters gives us the most return on that time investment. And again, we're doing this in both M82 and JWST. So I mentioned that some of our data has been observed. So what part of M82 has been observed so far? Again, it's this very central pointing in the near infrared. So this is not JWST, it is the Hubble image of the region of the spectrum. So we're looking forward to all of the things that JWST is going to tell us in much finer detail about this region. So with that, I'm going to summarize here for our live streaming audience. And the audience on Zoom and in the room, stay here, don't leave yet. But to summarize what I talked about, M82 and NGC253 are the 2 prototypical Starburst Galaxies in the local universe. They're really special, really unique laboratories to probe this physics of star formation just ramped up to a crazy scale. Both of them harbor these superstar clusters in their centers. Both of them have large-scale outflows of material emanating away from them. Galaxies in its first cycle of observation. And the team is working super hard analyzing and understanding the brand new data that we already have and eagerly awaiting the rest of them. And stay tuned for a press release of these data coming in the coming months. So with that, I will conclude and take any questions from the live stream, I believe.
I am not finding questions on Zoom. Do we have questions from Facebook?
No questions from Facebook.
Okay, so are there questions in the room?
There are.
Okay, we could go to those then, if somebody can move the mic around.
Thank you very much. First question, related to, I think it was the mapping of NGC253 being arranged. What's your certainty that that's the correct map? For us, you assign some value like that too.
You mean my certainty that it is actually arrayed?
Yes, and what you have to well.
Yeah, so if it's not a ring, it is ring like. So it may not be exactly the ring, it might have a warp or a twist to it that we can't quite tell, but it is extremely consistent with being a ring. And the fact this is expected from numerical simulations and models, these sorts of what we call them circumnuclear rings. They are rings that go around the center of the galaxy. Those are produced naturally by Mars in galaxies. And this is, I think, the first time we're seeing it in another galaxy in the data itself. Again, it's hard to explain.
Your turn.
It's really hard to tell this going on by just looking at an image like this. For example, you can imagine you can lots of shapes to that, you can combine it. So what helps us break the degeneracy is the velocity information. So we're able to measure the velocity of these clusters, in fact, that's what the color coding on the screen is showing. So from the mid-infrared spectroscopy, we will get some velocity information from some of the lines. We hope to get the velocity information from some of the lines. And so that might help with this. Although the spatial resolution of that will not be quite as good as the data that I'm showing here.
You were careful to point out the resolution of the almond data. What's the effective wavelength of that data?
So this is an wavelength of 850 microns. So that was some meter.
I remember about Zoe. You know, the amount of dust in the galaxy, that kind of thing. Is that what you, where you say there's a lot of dust? Is that? I don't remember. No. Measurement that you can use.
Could you repeat the question,
I
please?
don't know that Zoes are a super useful measurement in external galaxies. So it's a little bit hard to tell how much. So there's a couple of things going on here, right? There's the clusters themselves are very dusty, and that's what we're measuring in all the data. But there's also a lot of dust in the rest of the galaxy and the rest of the GT253 on the way to those clusters. And that's hard to measure because as soon as you sort of hit a wall of dust, you can't really tell how much is behind it. So we know there's a lot of it, and we know sort of we can estimate how much light is blocking, and that gives us an idea of how much dust there is. But actually measuring that is a sort of like that or an station is a little bit difficult.
So what is Starburst Galaxy not an one?
That's a great question. I think it's because M82 is so much smaller, and so it's more easily disturbed than M81. So if you notice in this image of M82, in fact, if you squint, this is not straight, it's formed. It has this twist to it. And that's an indication of this, you know, the impact of the final interaction having on M82. So I think it's just that because M82 is so much smaller than M81 and the other dwarf galaxy is too, they just don't impact M81 as much because it's so much bigger. And in contrast, they get hit really hard by this interaction causing the starburst.
Thanks, Bob.
Okay.
Yeah, Facebook. Tracy on Facebook asked, how long will this research be going on?
That's a great question. So I think for a very, very long time. So when you start a brand new facility, you never really know what you're going to see, and you have an idea of what questions you'd like to answer when you write a proposal. But the data always spur more questions. There are always more questions and more unknowns than there are answers. And so this is really the tip of the iceberg. Our data, I'll talk about this in a moment a little bit more, but our data will be made publicly available after a year. And so after a year, it won't just be our team that will be looking at them anymore. Anyone will be able to go in and download these data and look at them and make discoveries. And so I hope that these spur a lot of scientific longevity for many, many, many years to come.
So in the context of a galaxy, what exactly is it? It's dust. Is it sand or soil? Like I'm unable to understand that.
Yeah, that's a great question. So dust in the context of a galaxy, we think they're particles of silicates. So kind of like small rocks, and they span a whole range of sizes from, you know, nanometers or fractions of millimeters, all the way up to tons of things that form planets. So dust is sort of everything in between. Millimeter or sub-millimeter size dust, right? So very small shards of silicates that are forming galaxies. They're really important tracers, even though by mass they make up almost none of the galaxy by mass, but they have a huge impact in terms of, you know, blocking the light and in terms of tracing, where material is in the galaxy.
And then when you hypothesize that the cluster was in the form of a ring, did the relative brightness of those stars have any role in that hypothesis?
Not really. This was mostly done again based on the velocities of the clusters. So we're able to calculate the velocity, how fast each cluster is moving, and compare that to a model of one of these rings. And that's where we get this idea that they're a ring. It really is the velocity information that breaks a lot of uncertainties for us.
While you're on the topic of the ring, how is the velocity determined? Is that a one-time observation, and is it through some redshift type determination?
Yeah, so the way that we measure the velocity is through the Doppler effect. So if you're familiar with the Doppler effect, for sound, if you've ever heard an ambulance passing by you, when it's coming towards you, it sort of goes, meow. The same thing happens with light. So when light is coming towards you, the wavelength of the light will shift, it will go to a higher frequency, and when it's going away from the redshift, it will go to a lower frequency. And so because these objects, these star clusters are moving in the center of this galaxy as they're going around, some of them will be redshifted, the ones that are coming sort of red and orange here, and some of them will be redshifted, the ones that are going blue here. The way that we measure is we can detect spectral lines in all the data. And these are very narrow emission features for molecules, and we know precisely where those molecules emit from laboratory measurements here. And so when we see that line that is slightly red and where it's supposed to be, that's a direct measurement of how fast the gas in this galaxy is moving. And so it's not a one-time thing, we can go back and remeasure it. But that's how we determine the velocities.
In the superstar clusters, have you determined the size distribution of the stars in the cluster?
We have not. That's so that's a really hard thing to measure. We would love what we would really like to know is not the size distribution, is the mass distribution. So we think, although this is up in a little bit of uncertainty right now, that when you form stars in a cluster, you form a certain number of different masses of stars. And so you form way more low mass stars than you form high mass stars. And we think that that fraction of the stars that get formed in each mass is constant across the universe. And so that's actually how I can tell you how many stars are in these clusters, is I can assume how many stars of each mass are being formed and how much of I know what the total is, so how many stars are there. Now whether that function that determines how many stars of each mass get made is actually constant across the universe is a huge topic of research right now. But measuring that sort of empirically in these clusters is going to be really, really difficult because we can't see the stars themselves. We will never be able to see the stars themselves in these clusters. So we have to come up with other creative, indirect ways to try to get at that. But we would like to, but it's really hard.
Now, you mentioned that the obscuration factor of the dust is about 1 trillion times.
Mm-hmm.
If NGC 253 were totally devoid of dust, like how would it appear in the sky? Like, say, would it be as it is, it's an easy binocular object. Like, I suspect it would be a naked eye object and would be brighter than.
Yeah, I'm not sure exactly how much brighter it would be, but that obscuration is in the near infrared. If you go to the optical, that obscuration is many, many, many times greater, because dust is much better at blocking things in the optical than in the near infrared. And so if you were looking at it with binoculars, it would even be brighter than a factor of 1 trillion. So I'm not sure exactly what magnitude it would be, but it would be quite bright.
Well, you could figure like 5 times 5 magnitudes is 100 times.
Yeah,
So each 10,000 could be 10 magnitudes. 100,000 would be 15. A million would be 20.
yeah.
So now you're gonna go all the way to a trillion. I mean, that would probably be as bright as the sun. I mean, if that were to fit.
Yeah, it might be. It would be worth doing that calculation for real if it kind of does. That's true. There will be more time for questions from the room at the end of the next presentation too. But go ahead.
You mentioned that Sandage and Lines reported or suggested that this was a burst in N82 when they posted that in 1963, and they suggested that this was some kind of an event with an awful lot of supernovas. But wouldn't the supernovas all be going off at different times because those stars, when they form, do not all have exactly the same mass?
That's true, but the ones that will attract the most energy by far are the most massive stars, which will blow up first and not all at the same time. So you're going to get the biggest release of energy, the biggest input into the outflow when the most massive stars blow up, and they will blow up first. The rest of the sort of less massive stars that will still blow up as a supernova, they'll come later and sort of inject energy on a slightly longer time scale. But again, you're going to get that biggest effect of energy right at the beginning when your O-type stars all blow up.
I think that's all we have from here.
Okay, great. Then we can give Dr. Levy a break for a few minutes, and we have one other activity that Jim Knoll is going to present some awards. So we're saying goodbye, I think, and thank you to our people on social media for coming. We hope that you come back another time, and we hope that if you had sound problems tonight, we'll get those corrected. We are already planning some steps for that. So we hope to see you again for another First Friday TAAA meeting on, and we hope that you will be able to hear well, for that meeting and have a good experience. We are planning on posting a tape of this, and we are planning on trying to take out any place that there was a sound problem in that tape whenever we can do that. So if we're successful with that, you can check back later, and maybe we will have a recording if you did have difficulty hearing for this meeting. So thank you for coming.
All right, so as most of you know, Doug Smith is our astronomical lead coordinator. And so, and as such, he also participates in some of the awards. And so this is what we're going to present tonight. So this one is, this is the award presented to Douglas Smith for outstanding accomplishments in introducing the hobby of astronomy to others. It is the Outreach Award. It's the first level of the Outreach Award. So if Doug does more outreach, he can get additional levels. All right, and the second award is getting is for observing, imaging, and evaluating lunar features representing 7 geological epochs, awarded October 11, 2022. So this is the Lunar Evolution Observing Certificate. Now, for those of you that participate in the astronomical programs, you'll soon realize that this next award is a very significant one when you start doing lots of programs. I'm going to read the letter first. It says, congratulations on completing the necessary observing programs to satisfy the requirements of the Astronomical League's Master Observer Silver Award. I'm honored to be able to issue this award in your name. The silver level award, unlike other awards in master progression, requires quite a bit of sketching. That seems to limit the number of people that attempt to the required programs. I've met dozens of exceptional observers who have completed many programs, but they avoid all the programs that involve sketching. Our records indicate that your first award was received in 1978. I think it's fantastic that you have been involved with the Astronomical League observing programs for over 44 years. That was deserves a round right there. That's some serious dedication. Congratulations again, first guys, sincerely, David Whalen, Master Observer Progression Coordinator. And so the certificate is Master Observer Silver Certificate presented to Doug Smith for completing the requirements of the Astronomical League's Master Observer Silver Award on the 5th day of November, 2022.